Okay, thank you very much. My name is Waseem Haider. I'm an associate professor in the School of Engineering and Technology at Central Michigan University. So today I'll be talking on estimation of electrochemical charge storage capability of zinc oxide, copper oxide, and reduced graphene oxide nanocomposite. Okay, so just to give you a quick introduction, as you know, the supercapacitors, basically based on their charge storage mechanism, we have either a electrical double layer capacitor or we have a pseudo capacitor. And this mechanism, this charge storage mechanism, is basically is a material dependent, right? So either we can have a carbon-based material such as graphene or carbon nanotubes. They follow or electrical double charge layer capacitor, and then we have a metal oxides like the way we were talking about, like copper oxide, zinc oxide. So they have a storage mechanism of pseudocapacitors. So very quickly, so here the pseudocapacitor, basically they have a Faraday reaction, and then the transition metals, I have listed a few of them here, or even some of the polymers, they exhibit the pseudocapacitance. So basically, because of their low electrical conductivity and poor stability during the fast charging and discharging cycles, that restricts its widespread use. So very quickly here, moving on to introduction, is that we can make our hybrid capacitors. Basically, we try to combine the EDCLs and the pseudo-capacitors. So to eliminate the effect of agglomeration, because in EDCL and also the poor cyclic stability of pseudo-capacitor materials. So we are trying to have a combinatorial effect of graphene because it has a high surface area, high electrical conductivity, and then we can add those metal oxides to inhibit or agglomerations. So here is the experimental section. So we have 4 main types of materials we've prepared. So the first one is graphene oxide. We prepared from graphite powders. I'm going to be talking about it in a little bit. And then we have second type of or electrode is going to be copper oxide, reduced graphene oxide. The third one is going to be zinc oxide, reduced graphene oxide. And the fourth one is a combination of all 3, which is basically zinc oxide, copper oxide, and reduced graphene oxide. So after we have synthesized these powders, so we're going to be using a wide range of characterization techniques such as SEM, TEM, XRD, DSC, TGA, and also XPS. And then we have studied, we did electrochemical analysis. We have done quite a bit of it, but just because of the time slot, I'm just only talking mainly on cyclic voltammetry and galvanostatic charge discharge on all of those 4 electrodes. So here is the synthesis of powders. So on the top row, you see that we have taken a graphite, and then we have converted into graphite oxide, and then the graphene oxide basically by the very well-known improved Hummer's method. And once we have that, we have added copper oxide onto that reduced graphene oxide. So this is this is one type of nanocomposite we made. So basically, these copper oxides are in the form of rods. I'm going to show you some SEM and TEMs in a little bit. So these copper oxide is coming in the form of rods, and then we have a zinc oxide, reduced carbon oxide, reduced graphene oxide, which is basically spheres. And then finally, we have the ternary nanocomposite where we have zinc oxide, copper oxide, and reduced graphene oxide, where you could see a combination of rods and spheres right on the reduced graphene oxide. So this is about the synthesis. Okay, so now as far as the electrochemical studies are concerned, so we have prepared our electrodes, from those nanocomposite powders. We have about 85 weight% of those powders, and then we have a black carbon and also a polymer PVDF, about 5%. And then we have made a slurry and coated onto those coated onto those nickel mesh structures. And then we dry them for 80 degrees centigrade, and then using a hydraulic press, we basically created those electrodes so that they can be used as a working electrode. We have used this Gamry potentiostat, as I said before. So we have a reference electrode as saturated calomel electrode. Then we have a platinum coil as auxiliary electrode, and we have been using 0.9 molar sodium sulfate. And we always, every time when we do experiments, we were purging nitrogen for about 20-30 minutes just to, to remove the dissolved oxygen. So here is TEM, electron micrographs. The first one, you could see a sheet for graphene oxide. And then in B, you see a copper oxide, graphene oxide. You see some rods in here. So here is a zoomed image. So you could see, so the diameter of these rods are approximately 50 nanometers or so. And the C is basically zinc oxide, reduced graphene oxide. You could see these spherical structures. And then we do see some agglomerations where you see a lot of rods and spheres together for zinc oxide, copper oxide, and reduced graphene oxide. So here's the XRD pattern for all four of them. So we have graphene oxide, copper oxide, and then zinc oxide, and then the combination of ternary composite. So just wanted to make sure that, and then we also have infrared spectroscopy, by the way, because we are using this. There was a diamond crystal in ATR, so in IR. So this is what it is representing, and then we have a signature peak for carbon oxygen double bond, and then we also have a zinc oxide and a copper oxide peaks as well. So basically, we are trying to use all different types of characterization techniques to make sure that we have zinc oxide and copper oxide on our graphene. So these are TGA and DSE analysis, and also the TGA and DGG data, so which is a differential calorimetry. So curves both for geo and also for the nanocomposites. So I try to use the same colors so that you can have some representation for each one of them. And here is field emission scanning electron microscope images we have used. We try to use this, how do you call it? Like these images, in a sense that we try to use scanning so that we can find out where the copper is more agglomerated and where zinc is more agglomerated, and so on and so forth. So this also gives us some representation where you could see that we have a copper in these areas, and then we have a zinc in some of these areas, and so on and so forth. Okay, and then we have done a detailed XPS analysis just to make sure that if we have those, copper in the form of oxide and also zinc in the form of oxide. So we also had first the survey spectra, and this TEM was also coupled with the EDS so that we can get just some EDS analysis in general. And so these are the EDS analysis based from TEM also, and also from XPS, from survey spectras. So here we have high resolution spectras because we wanted to make sure that for all the different ones. So for example, for oxygen, we wanted to make sure that it's approximately at 528 or so we have an oxygen peak. So if it's a single bond, double bond, and if they are from oxides, what kind of oxide is? Mainly it was copper +2 and Zn +2. So, and also based on this difference here, for example, from zinc, the difference was approximately 23.04. That also gives you some impression that the zinc was also present in the oxide form. Okay. Yeah, so we have all of these ones, and then just jumping onto the electrochemical analysis. So we did this cyclic voltammetry. You could see the cyclic voltammetry. So here we have used the different scan rates from 1 millivolt per second all the way to 100, and then we have I've just selected 25 millivolts curve from each one of them, from A, B, C, and D. From A, B, and C, remember, A is with the copper, reduced graphene, B is zinc, and the C is a combination of all three. So you could see that the loop is much bigger for zinc oxide, and then this we try to verify this one also from charging discharging experiments, just to make sure. And we find out that it's basically the pseudo capacitance behavior of zinc oxide, reduced graphene oxide. It's basically because of this absorption and desorption of these species during the charging discharging experiments. So this is what I was just trying to say, that we have the species here, we have the diffused ions between the layers, and during the charging and discharging, there is absorption and desorption taking place. Now, similarly, when you look at the specific capacitance, you could see the green ones, these histograms, the green ones is representing the zinc oxide, reduced graphene oxide. It is much higher. This is just below, this may be right around 350 of specific capacitance. But this was low for copper oxide, and also for the zinc oxide, copper oxide, reduced graphene oxide altogether. And again, going to the charging discharging curves for all three composites, and again, you could see we have done at the current densities of 400. This should be 400, so it should be 400, 500, 600, and 700, and you could clearly see that that at 400 you could see the zinc oxide is showing a really different behavior from other ones altogether. So just quickly jumping onto those, we have a little bit more data, but I just restricted here just to show you that the specific energy, for example, for zinc oxide, reduced graphene oxide, was approximately about almost 22 or 21.9 at 400. And then we also have a high power density, for example, at the same one, which is approximately maybe around 130 or so. And similarly at 700, you could see that the specific energy is maybe right around 7 or 8, while the power density is maybe approximately right around 195 or so. Again, these are basically the we got these higher values, higher specific energy values, and high power density values for zinc oxide, reduced graphene oxide, when compared with this ternary or the other binary, which is copper oxide, reduced graphene oxide. So these are all the results, and then very quickly jumping on to conclusions, that we have prepared all these three nanocomposites by a single path synthesis route, and we have studied the morphology of these nanocomposites, with the electron microscopies, and then we have studied these nanocomposites using various different techniques, characterization techniques, and finally the higher specific values were exhibited by zinc oxide, reduced graphene oxide. So with that being said, thank you very much. I really appreciate it.